Namaste, welcome to Goglides. In today's video, we're diving into how to create a Jupyter notebook for the MNIST dataset using Red Hat Openshift AI. We will walk through launching a workspace with TensorFlow, developing a model with Keras, and visualizing our result all inside Openshift AI. By the end of this video, you will learn how to spin up a notebook using Openshift AI, load and pre-process the MNIST dataset, train a neural network using Keras, evaluate the model locally from the Jupyter notebook itself, deploy the model in OpenShift serving on time, and finally visualize the model using a web application and make the prediction. So let's get it started. Let's log into our OpenShift AI dashboard from this link, Red Hat Openshift AI. It's already logged in. Once you are in, create a project or use an existing project from Data Science project menu. Click on Create Workbench. And from here, launch a notebook. So I'm going to call it MNIST Handwriting Recognition Development and select a image. So I'm going to use TensorFlow for this. You can select a version 2024.2 and select a container size. I'm going to use medium for now. There is no GPU required for this development. It's a very lightweight model. And there is no environment variables required for this workbench. So we're going to select the default values for now. And I think persistent storage 20 gigabyte is fine. It's a very lightweight and dataset is not that big. There is no data connection required. So let's create new workspace. It's now starting. As you can see in events log as well, this is 24% complete or 72, 18, 96% there now. All right, so this is up and running. So let's navigate to these notebooks. I'm going to use the default credentials for this. And this is the first time we are going to see authorized access. So let's allow all selected permission. All right, so this is our Jupyter notebooks. So let's start creating models. All right, so let's start developing the notebooks. This line imports the MNIST dataset, a classic collection of 70,000 handwritten digit images 0 to 9, split into training and test sets, and we'll do that later. Import the sequential models from Keras, which let us build a neural network layer by layer. Import the core layers used in convolutional neural network CNN. Con2D applies convolutional filters to the image to extract features. Max pooling 2D downsamples the image to reduce computation and overfitting. Dense fully connected layers for classification. Flatten convert the 2D features map into 1D vector before passing to the dense layer. Let's run this one. This line loads the MNIST dataset, which contains 60,000 training images and labels, 10,000 test images and labels. Each image is 28 by 28 grayscale image of handwritten digit from 0 to 9. Let's run this. This will load. Now this line reshape the 2D image to 3D by adding channel dimension, 1 for grayscale. CNN in Keras expect input shape in format height, width, and channel for 60,000 images. And same is valid for testing the image as well. This line convert pixel values from integer 0 to 255 to floating point numbers, divided by 255 to scale the values between 0.0 and 1.0, which helps the model train faster and more efficiently or effectively. All right, let's run this one as well. The original labels are integer from 0 to 9, example 5, 3, 9. To categorical converts each label into one hot encoded vector. Example, if the original label is 3, it becomes 0, 1, 2, 3, and we paste 1 as 3 here, and then rest is 0 there. The format is required for multi-class classifications when using the categorical class entropy loss function. It helps the model understand that each image belongs to 1 out of 10 possible categories. This line initialize sequential model, which means layer will be added one after another in a linear stack. Adds Con2D layer with 32 filters of size 3 by 3. Activation ReLU introduces non-linearity. Input shape 28 by 28 pixels. One is 10 for channel dimension, which is a grayscale image at the moment. This line applies max pooling with 2 by 2 window. This reduces spatial dimension downsampling, helping with speed and overfitting. And we're also adding second set of convolutional and pooling layers to extract deeper features. And here we're finally transitioning to fully connected layers, which flatten the 3D features map into 1D vector. This is necessary before feeding data into dense, fully connected layers. This line represents a fully connected layer with 128 neurons and ReLU activations, which learns complex patterns from the extracted features. This is our output layer with 10 neurons, one for each digit. Softmax activation turns the output into a probability distributions. Here, we're simply compiling the models. We're using Adam optimizers. Adam optimizer is efficient and adaptive. Categorical cross entropy is the loss function used for multi-class classifications. And this section tracks accuracy during training and evaluation. All right, so let's initialize this value as well. This sets a data augmentation strategy where width shift range equal to 0.1 and height shift equal to 0.1 means that each image can be randomly shifted by up to 10% horizontally or vertically. This helps the model generalize better by simulating slight variation in handwriting. DataGen prepares the data generator using training images. It computes any statics required for normalization or augmentation. Not strictly necessary here, but it is still a good practices. Now we are training the model with augmented data. Data flow creates an infinite stream of augmented image batches, 32 at a time. Steps per epoch tells Keras how many batches to process in one epoch, this entire line. Epoch 10s means the model will train over 10 full pass through the dataset. Why this matters? Instead of training on the exact same images every epoch, the model sees slightly modified version, which helps it become more flexible and accurate. All right, so let's start the training process. It's going to take some time, almost 2 minutes. As you can see, accuracy is increasing here, loss is decreasing, and then we are in epoch 1 by 10. We are in epoch 3 by 10 now. Accuracy is 96% already there. Loss is 0.10, 10%. Give it some time. We are almost there. Now the accuracy is 98% already. And this is complete. All right, so this line evaluates the model on the test dataset, which the model has never seen during training. It returns two metrics, test loss and test accuracy. So let's run that. And this will also save the model into this folder. So here, as you can see, test loss is 0.02, and then test accuracy is almost 99% there, which is pretty good model. Here, we're saving the entire model, architecture plus weight training config into a H5 file. This allows you to reload it later for prediction or fine-tuning without retraining. And this is where you can find that model. Now that our model is trained and safe, let's use it to make prediction on new handwritten digit images. First, we load the trained model from DIX using load model. This gives us the exact same model we trained earlier, ready for inferencing. What we have built so far is perfect for local training, evaluation, and testing. But what if we want to use this model in production, inside an app, exposed through an API, or running on a server? We need to convert this model into a format that's optimized for production environment. Let's start converting this model into a ONNX format, and then I will download this model, upload into a S3 bucket, in this case Minio, and then we will deploy this into Red Hat Openshift AI multimodal servers. I'm going to use Intel OpenVINO model server for that. For this, what I need to do is, first of all, convert this model to a TensorFlow submodel format. And here is the code base which will help you to convert this into that format. First, we load the model using load model functions. We set compile false because we only need it for inference, not for retraining. Then we convert into TensorFlow submodel format, which is the standard format TensorFlow use in production. It saves the model architecture, weights, and computation graph in a directory called model MNIST, and this is the location of that. This format is the starting point for deploying the model on platforms like TensorFlow servings, OpenShift AI model servers, or cloud APIs. The step 2 is installing this library called TF2ONNX, a tool that converts TensorFlow model into ONNX format, short for Open Neural Network Exchange. After this, with one command, we convert our model from TensorFlow's submodel format to an ONNX. The offset 13 flag ensures compatibility with most runtime environments. Why ONNX? ONNX is designed to make your model portable. Once it is in .ONNX format, it can be deployed in many environments like NVIDIA's Triton, inference servers, Microsoft ONNX runtime, or even OpenShift AI model servers like VLLM, OpenVINO model servers, or custom endpoints. It's a powerful way to break free from single framework and make your AI models cloud and hardware agnostic. All right, so let me run this section here. This is now complete. And if you refresh this page, as you can see, MNIST physics save folder is there now. Now we have to install this TF2ONNX, TensorFlow to ONNX, and this is now already satisfied. And simply run these sections which convert this folder MNIST physics save to a ONNX. So let me run that. It's going to take some time. And as you can see, now the model is saved here, and you will see that model shortly here, physics ONNX. So that's the model we just saved. Now simply download this model, and then we're going to upload that model to S3 bucket. So let me create a buckets for that, MNIST demo, and then we can call it 2. Let's create a bucket. Then go to object browser, MNIST demo 2, create a path. Let's call it handwrite. Create it. Let me upload a file. We just downloaded that. File is also uploaded, and this file is here now. Okay. So next process is we have to navigate to Red Hat Openshift AI. Let's create a project called MNIST handwriting. Let me create it, and then let's navigate to model section. From here, let's create a multimodal servers because this is a very lightweight model. We don't need like dedicated hardware for this one. We can use same model servers host multiple small models like this one. So let's select this. And then I'm going to create a model servers now. I'll call it MNIST. Select one runtime. So I'm going to use OpenVINO for this. You can also select Triton if you prefer that, but this is a custom model servers. It's not supported by Red Hat Openshift AI by default. You have to basically import it. So I have imported this one. Then let's select a model server size as medium. Make deploy model available through an external route. And for now, I'm going to disable token authentication, and we can enable it later quickly as well. So let's disable that for now for quick testing. Let's click add. And then now model server is ready. Then we have to deploy this model, right? So the model name is anything. So I will call it MNIST. Framework is ONNX. That's the model format we choose. And then I need to create the connections. So let's select S3 compatible because it's available in our Minio. I'll call it connection name as Minio. Then use the valid access key and valid secret there. The Minio service is available on NetSentinel namespace. You can check this as well. And this is exposed at port 9000. And then reason is anything is fine. But technically, you can use any object storage here. So if you are preferring AWS S3 bucket, then you can also pass that information. And then bucket name is MNIST demo 2, and it requires a path. So you can pass the full path here or like this, or you can simply say handwriting as well. Without slash here, it will go up to bucket and then folder name. And then if there are multiple models, then pass the full name. Otherwise, you can simply say handwriting as well. Okay. Then click on deploy. Now it's going to take some time. Then here, this is the endpoint URL which you can access it. For now, let me go here and then let's check that progress from this handwriting. This is a project we just created. And as you can see, this is now up and running already. Everything looks good actually. Let's go here and looks like this status is also passing now, right? So you can technically browse this in the browser now, but the method is not allowed, which is okay. It's expected because we need to pass other information. Now, what we can do is let's go back to this notebook again. So I've created a function or sections of notebooks where you can pass the endpoint URL. So I copied that endpoint URL here and simply paste that. This is the location of that. I just copied this section from this. And we're going to use the preprocessed image functions. And then I'm going to iterate data folder. This is a data folder. All the JPEG file it will collect, convert into a payload. It will have a data list, flatten, and then send that to this endpoint URL. So this is the endpoint URL we just copied where the model is available, and pass the request payload, converted payload. So let me run this quickly. And as you can see now, 5 is predicted as 5, 8, 1, 1, 7 is also predicted as 7. So it looks like everything is working fine. We deployed that model into a open window model servers and use the API call to send all the JPEG files and then predicted the actual outcome using that model servers. I have also created a web application which can consume these API endpoints. So let me clone this in my local machine right now. So this is the location of that. All right, so it's not clone. Let's navigate to that folder. Let's navigate to notebooks, handwriting. There is a MNIST web UI. Let's do one thing here. So we need a virtual env. Let me create that. Let's source it and activate. Then you can install all the requirements for these web applications. It has a very basic requirements. You still need that one. So let's install this in this virtual env. Right, so this now done. Now let me open this app.py. Then we have to update this endpoint URL with our valid endpoint URL. I'm going to copy that from this browser and then change that value here. Let's comment these sections. We can say point underscore URL and then simply paste that value. Now let's save the file and simply run this app.py. Now this is up and running. Now we should be able to open that same URL here, localhost 5000. All right, this is now available. So let's try to hit that or draw something here. Let's predict it. So it looks like the predicted digit is 1, right? Let's clear it. Let's try to draw something here. 8 is predicted as 8, 9 predicted as 9. You can also validate that whether it's hitting the correct endpoint or not by enabling the token for this. The model servers require token authentications. Let's update it. Now this endpoint is secure, right? So if you try to browse this in your browser, it will basically redirect you to login page, right? This means I don't have any authentication enabled in this application. So if I hit predict this one, you should see something like this. This is not working right now because that authentication is enabled. We can quickly disable it. So it's that easy here. Now let me try that again. And then it's predicted perfectly, right? Looks good. All right, let's wrap things up. In this video, we went through the complete life cycle of an AI model from training to production. We built and trained a convolutional network CNN using the MNIST dataset inside a Jupyter notebook on OpenShift AI. We evaluated the model, ran prediction so it accurately recognized handwritten digits. We convert the trained H5 model into TensorFlow shape model format. Then we export it into ONNX, make it portable and ready for production deployment. And finally, we deploy the model, making it available for real-time inference in a production environment as well. And we ran inferencing from the notebooks as well as from web application. So this is a kind of end-to-end pipeline that mirror how AI models are built and deployed in real-world system from idea to impact. Whether you are testing a model in a notebooks, scaling it in OpenShift AI, or exposing it as an API, this workflow set the foundation. Thank you so much for watching. If this helped you, please subscribe to Goglides. Have any questions or want to see the next steps? Drop a comment below. Dhanyavad, and I'll see you in the next one.